Welcome back to the deep dive. It is genuinely good to have you here with us.
It is.
Today, we are tackling a concept that, well, it often feels like secret knowledge. Or at least knowledge that feels like it should be locked away in some engineering vault somewhere.
Hmm.
You know those moments where you look at a problem, it could be a stalled project at work, a piece of broken tech, or even just a logistical nightmare in your kitchen, and you think there has to be a scientific way to fix this.
Oh, we've all been there,
Yeah.
staring at the wall, waiting for that light bulb to go on.
Waiting for the light bulb, hoping for inspiration to strike.
Yeah.
Exactly. We rely on inspiration. But today is about rejecting that reliance. We are exploring the idea that innovation is an algorithm, not a mood. But before we get into the machinery of that, I have to acknowledge the engine powering this specific deep dive.
Right.
This conversation is brought to you by the incredible content from @IDMechanics9 on YouTube.
A genuinely fantastic resource if you're interested in engineering, systems thinking, or just, how the world is put together. It's amazing.
It is absolutely essential.
Yeah.
If you are the kind of person who listens to us, someone who wants to understand the why behind the what, you really need to be subscribed to that channel.
Mm-hmm.
I'm serious. Pause this right now. Well, maybe don't pause this for too long, but go subscribe to @IDMechanics9. They have links in their description for some specific innovation tools that we are going to touch on, and I promise you it is worth your time.
And while you're there, or even while you're listening to us right now, leave a comment. We really want to know which of these principles, which one really clicks for you.
We do, and the reason we are pushing at IDMechanics9 so hard is because their philosophy is really the backbone of today's deep dive. They believe, and we believe, that innovation is a repeatable process.
It's not a eureka moment.
You don't wait for lightning to strike. You follow the map.
And we have a very specific map today. We're continuing our journey through TIZ.
TIZ, the theory of inventive problem solving.
Correct. So in previous dives, we've looked at the foundational principles, 1 through 10. Today, we are getting into the weeds. We are looking at principles 11 through 20.
And for anyone thinking, oh, a list of principles, that sounds a bit dry, let me just stop you right there. This is a cross-industry analysis. We are talking about everything from why aerospace landing gear doesn't just, explode on impact,
Right.
to the atomic structure of your iPhone screen, to how skyscrapers get built in crowded cities.
The mission for this deep dive is, well, it's simple. We want to show you how these 10 principles help you solve contradictions.
Contradictions. Okay, that is the magic word in TRIZ, isn't it?
It is the central dogma. A contradiction is when improving one part of a system breaks another part. It's that classic trade-off.
Like, you want a car to be faster, so you add a bigger engine.
Right. But now the car is heavier, which makes it slower in some ways and burns more fuel. That is a contradiction. Most people just compromise.
Find a middle ground.
TREZ says, don't compromise, solve it.
I love that. Don't compromise. So let's jump in. We are starting with a section I'm calling the safety net. This is covering Principle 11 and Principle 16.
Dealing with the inevitability of failure.
Okay, let's start with Principle 11. Beforehand cushioning. To me, this sounds like putting pillows on the floor before you try a backflip.
That is. That's actually a surprisingly accurate physical analogy.
Mm-hmm.
But in engineering terms, it's about proactive reliability.
Okay.
The core concept is moving away from reacting to a problem after it happens, and instead assuming the problem will happen with 100% certainty and building a mechanism to absorb that shock before it can cause any damage.
So it's strategic pessimism.
I like that. It's managing kinetic and systemic energy. Let's look at the aerospace industry. Consider the landing gear on a modern airliner.
Okay, landing gear. I mean, talk about a high-stakes environment.
The contradiction here is intense. You need a structure that is incredibly rigid to hold the static weight of a 200-ton aircraft just sitting on the tarmac.
Mm-hmm.
It has to be stable. But if it's too rigid, if it's just a solid steel column, what happens when you hit the runway at, say, 160 miles per hour?
It snaps, or it just punches right through the wing structure. Has to.
Exactly. A rigid structure transfers 100% of that shock energy to the frame. Catastrophic failure.
Yeah.
So you need rigidity for support, but you need flexibility for impact.
And the solution is the oleopneumatic strut.
The oleopneumatic strut, that's it. It's a shock absorber that very cleverly combines two distinct states of matter to solve this problem.
Oleopneumatic. Okay, break that down for us.
So oleo refers to oil hydraulic fluid. Pneumatic refers to gas, usually compressed nitrogen.
Why both? Why not just a big metal spring? I mean, cars have springs.
Well, a spring stores energy and then it bounces it back. That's what springs do.
Okay.
If you landed a massive 747 on giant steel springs, the plane would just bounce down a runway like a pogo stick,
Yeah.
which is, incredibly dangerous.
Yeah, I can see that being a problem.
You need to dissipate the energy, not just store it and release it. You need to just
Sure.
go away.
Okay, so how does the strut do that? How does it get rid of the energy?
So when the wheels hit the tarmac, the strut compresses.
Yeah.
The gas, the nitrogen, acts as the spring. It compresses to absorb the initial volume change. But at the same time, the hydraulic fluid's being forced through these tiny calibrated holes, they're called orifices, inside the piston.
Oh, like pushing water through a syringe, that resistance you feel?
That is exactly it. And pushing fluid through a small hole creates massive friction. That friction turns the kinetic energy of the landing, the violence of the impact, into heat.
Ah.
The heat then dissipates into the metal of the strut and the air around it. So the plane doesn't bounce, it just settles. The strut cushions the blow by converting violence into heat.
That is brilliant. It's literally cushioning the aircraft using fluid dynamics. Just incredible.
And Principle 11 goes even further. It's also about redundancy. Think about military aircraft or spacecraft. They don't just hope the landing gear deploys.
Right. If System A fails, System B wakes up. Is that the idea?
Precisely. And if System B fails, there might be a gravity drop manual release or even a backup parachute. It's all about preparing for the worst-case scenario so that a single failure doesn't become a catastrophe.
You're cushioning the reliability curve.
Exactly. You assume the primary system will fail, so you cushion that failure with a backup.
That makes perfect sense.
Yeah.
But let's bring this down to earth. I mean, literally into our pockets. Smartphone screens.
Yes. The modern miracle of Gorilla Glass.
This is a classic contradiction we all live with. We want our phones to be sleek, light, and thin. But thin glass is naturally brittle. So how do you cushion a piece of glass that's, barely a millimeter thick?
You use chemistry to build the cushion inside the atomic structure of the glass itself. This is fascinating stuff. It uses a process called ion exchange.
Okay, walk us through that. I'm picturing some kind of microscopic swap meet.
That's pretty close. Imagine the glass structure is originally filled with lots of sodium ions, and sodium ions are relatively small. Now, the manufacturer takes this sheet of glass and dips it into a bath of molten salt that's full of potassium ions.
A hot salt bath. Got it.
And here's the trick. Potassium ions are significantly larger than sodium ions. In this hot bath, the small sodium ions migrate out of the glass, and the big, bulky potassium ions squeeze themselves into the spaces where the sodium used to be.
It's like trying to fit a basketball into a hole that was made for a tennis ball.
Exactly that.
Yeah.
And because they're all jammed in there, they create a layer of high compressive stress on the surface of the glass. The glass is literally pushing against itself, trying to hold itself together.
And that tension is the cushion.
Yes, because glass breaks under tension when you pull it apart, but this glass is already under compression. So if you get a tiny scratch on your phone, say from your keys, that scratch creates an opening.
Right, which would normally spread into a crack.
Usually.
Yeah.
But here, the internal pressure from those big potassium ions squeezes the scratch shut. It stops the crack from propagating.
That is so cool. So it's not just hard glass. It's glass that has been chemically pre-stressed to be tough.
It's proactive cushioning at the atomic level.
Okay, let's pivot this to IT for a second. I feel like cushioning in IT just means backing up your files, which, I don't know, it feels a bit basic for a deep dive.
It is basic if you do it manually once a week. But Principle 11 pushes us to be proactive, to be preemptive.
What do you mean by preemptive? It knows I'm about to spill coffee on my laptop.
Ideally. But think about a big server farm. They use something called SMART technology. That's self-monitoring, analysis, and reporting technology.
Okay.
The system is constantly monitoring the health of all the hard drives. It's looking for these really subtle signs, tiny temperature spikes, delays in spin-up time, an increase in read-write errors.
But seeing the symptoms before the heart attack.
That's it. And the moment it sees those signs, before the drive actually fails, it automatically triggers a data migration. It starts copying that data over to a healthy drive. It's cushioning the fall before the drive even realizes it's dying.
That is smart. It moves the entire process from recovery to prevention. Okay, this connects nicely to the next one. Principle 16, partial or excessive actions.
Right. This principle often confuses people at first because it sounds inefficient.
It does. It sounds like it's encouraging us to be sloppy, like just do a half job.
And in a way it is, but it addresses a very specific problem. What if precision is impossible or just way too expensive? What if hitting the target exactly 100% takes too long, or costs too much.
So the advice is, don't even try to be perfect.
The advice is, if 100% is hard, do 110%. Or maybe 90%, do slightly more or slightly less, and then just fix the difference. It's often cheaper to clean up a little mess than to never make one in the first place.
Give me a concrete example of that.
Manufacturing is the classic use case, casting and molding. So imagine you are making a complex engine part by pouring molten aluminum into a mold.
Okay, I'm with you.
It is incredibly difficult to pour exactly the right amount of metal needed to fill every tiny corner of that mold without spilling a drop or leaving a little air pocket. If you try to be that exact, you risk an incomplete pour.
Which ruins the entire part. You have to scrap it.
Right. So you apply Principle 16, excessive action. You intentionally overfill the mold. You design it with a sprue or a runner system that fills up with all the extra metal.
So you're guaranteeing the mold is full by wasting some metal.
You're guaranteeing quality.
Right.
Yes, you have this weird stick of metal sticking out of the part that you have to cut off later. That's the trimming of the excess. But that trimming process is cheap and easy. Scrapping a complex engine block because it has an air bubble inside, that's expensive.
It's a great trade-off. Waste a tiny bit of material to save the whole product. I feel like we do this in real life all the time, painting a room.
Oh, absolutely. This is the painter's cape principle.
Right. If you have ever tried to paint perfectly up to the edge of the trim without using tape, you know it's just a nightmare. You're trying to be 100% precise with a wobbly brush.
And you inevitably fail. Your hand shakes, you get a little paint on the trim, or you leave a tiny gap. It takes forever.
Exactly. So what do? You put tape down. You paint over the tape. That's the excessive action. You paint more area than you actually need to. Then you peel the tape back, and you have a perfect, crisp line.
You accept the excess to achieve the precision. You're basically outsourcing the precision to the tape.
Outsourcing the precision. I love that phrasing. Okay, what about service industries? Can you use excessive action when you're dealing with people?
Definitely. Think about overcompensation in customer service. Let's say an e-commerce company messes up your order. It's 3 days late.
Okay, I'm annoyed. I'm already composing the angry email in my head.
Right. So they could just fix it. Deliver the package, that's 100% of the action, but the customer relationship is damaged. So to fix the relationship, they go to 110%.
How so?
They refund your shipping costs, and they give you a 10% discount on your next order. They overdo it.
They do. They go beyond just fixing the problem.
They overdo it intentionally. That excess acts as a buffer to absorb the customer's anger and hopefully restore their trust. It turns a negative experience into a wow moment.
That's really smart. And there's one more example from the notes here that I found fascinating. Controlled burns in forestry. This seems so counterintuitive. You set a fire to stop a fire.
It's the ultimate partial or excessive action in nature. Forest managers know that if fuel, dead wood, dry leaves, if that builds up over years, a wildfire started by lightning will be absolutely uncontrollable.
Right, it'll be a catastrophe.
So they apply an action that seems excessive. They burn the forest themselves, intentionally, but they do it in a controlled way, under specific weather conditions. By burning more than is strictly necessary right now, they remove the fuel source and prevent a catastrophic high-intensity burn later on.
It's incredible how these principles apply to molten metal, to house paint, to customer feelings, and even to entire forests.
It really shows that these patterns of problem solving are just universal.
Okay, let's move on to section 2. We're talking about working with the environment. This covers principles 12 and 14.
Moving from safety buffers to shaping our physical world to make things easier.
Principle 12 is equipotentiality, which is a $5 word if I have ever heard one.
It is a mouthful, but the concept behind it is remarkably simple. Don't fight gravity.
Break that down for us.
Well, in physics, potential energy is the energy stored in an object because of its position. If you lift a heavy box from the floor to a table, you're doing work against gravity. You are increasing its potential energy.
Okay.
Equipotentiality just means keeping things at the same level, the same potential, so you don't have to waste energy lifting them up and then putting them back down.
So basically, stop lifting heavy stuff if you don't absolutely have to.
That's the core of it. Think about a factory floor in the early 1900s. Machinery might be at all different heights. A worker would have to lift a heavy part from a cart on the floor, carry it up a step, machine it, then put it back down.
Exhausting and terrible for your back.
Exactly. So we apply equipotentiality. We build transfer lines and walkways at the same level as the machinery. Or look at a modern warehouse with its conveyor belts.
Ah, the conveyor belts.
The belt keeps the heavy package at a consistent height, usually waist height, through the entire process. The worker doesn't have to bend down to pick it up or reach up to place it. It minimizes fatigue by essentially neutralizing gravity's effect on the worker.
My favorite example of this has to be the car mechanic.
The hydraulic lift.
Yes! Think about it. The car is on the ground. The mechanic needs to work on the undercarriage. They could lie on their back on one of those little creeper things and scoot under there.
Which is uncomfortable. It limits your leverage, it limits your vision, and it's just awful for your neck and back.
Right. Or they use a lift. They raise the car. But notice what they're really doing. They aren't just lifting the car. They're bringing the work to the mechanic's eye level. They are creating an equipotential state between the work zone and the human body.
That's a great way to put it. They're adjusting the environment so the human doesn't have to contort their body. We see the exact same logic in healthcare with adjustable hospital beds.
Oh, that's a huge one for nurses.
It used to be that nurses had to constantly bend over to treat patients or physically lift them to move them. Back injuries were, and still are, the #1 occupational hazard in nursing.
So the adjustable bed brings the patient to the nurse.
Exactly. Or it lowers the patient so they can get out of bed easily on their own. The bed adjusts to create the optimal equipotential level for whatever task is at hand.
There's also a note here about pneumatic tubes. You mean those things at the bank drive through?
Yes. Or in older hospitals, they use them to move blood samples between labs. It's a great example. It uses air pressure to suspend the capsule. It minimizes friction and, in a way, it eliminates the heavy lifting of physically transporting materials across a large building. It just floats them on a cushion of air.
I love those things. They feel like this cool retro future magic. Okay, let's look at principle 14, curvature.
Also known in some of the textbooks as spheroidality.
I think I'll stick with curvature. This basically says, nature loves curves, so maybe we should too. You know, factories build boxes, but boxes are inherently weak.
Well, corners are weak. That's the engineering reality. In any structure, stress tends to concentrate at sharp corners. We call them stress risers.
And the classic, tragic example here is airplane windows.
This is such a vital lesson in aviation history. The early jetliners, specifically the de Havilland Comet, had square windows, just like a house window.
Seemed logical at the time. Windows are square.
But airplanes are pressurized tubes. As the cabin pressurizes at high altitude and then depressurizes for landing, the metal fuselage expands and contracts. It actually breathes with every single flight.
And what was happening at those corners?
At the sharp 90-degree corners of those square windows, the stress built up intensely.
Yeah.
It had nowhere to go. It couldn't flow around the corner. Eventually, the metal fatigued, tiny cracks formed, and the planes literally disintegrated in midair.
That is just terrifying.
It was a terrible tragedy. The solution was Principle 14, curvature. Look at any plane you fly on today. The windows are round, or at least oval with rounded corners.
Because the curve distributes the stress evenly.
Exactly. A curve allows the force to flow smoothly around the opening. There's no single point for that stress to gather and start a crack.
So it's not a style choice, it's a survival mechanism.
Absolutely. But curvature isn't just about strength, it's also about aerodynamics. The teardrop shape.
The most aerodynamic shape in nature, right?
A falling drop of water. We now use incredibly powerful software, computational fluid dynamics, or CFD to model cars and planes to be as curved as possible. A brick fights the air. A teardrop slips right through it.
And that's why all modern cars have those sloping windshields and rounded noses.
Even the side mirrors are curved. If you drove a perfectly boxy truck at 80 miles an hour, your fuel consumption would be astronomical because you were just fighting air resistance the whole way. Curves mean efficiency.
And then there's architecture, domes and arches.
The arch and the dome are absolute miracles of curvature. I mean, think of the Pantheon in Rome. It's this massive open space with no internal columns holding up the roof.
How does that roof stay up? It's made of concrete.
It's the curve. A flat stone or concrete roof would snap under its own weight. Stone is terrible at handling tension. But a dome transfers that weight down and out to the thick walls at the base. It keeps the stone in compression, which is where stone is incredibly strong.
It feels like once you start looking for curves, you just see them everywhere. Even in my hand.
Consumer ergonomics. Exactly. Look at your smartphone. It's a rectangle, sure, but look at the edges.
They're rounded.
Look at the back. It's often slightly curved. Why? Because your hand is not a flat block. It's curved. Devices that fit the geometry of the human body are just more comfortable to hold and use for long periods.
And what about curved TV screens? Is that just a gimmick?
You know, there's actual science to it. If you're sitting in the sweet spot in the center, every point on a curved screen is the same distance from your eye. It creates a more immersive experience because your eye doesn't have to constantly refocus as it moves from the center to the edge.
Interesting. So curves give us strength, speed, comfort, and even immersion.
Not bad for just bending a straight line.
Not bad at all. Okay, let's shake things up a bit. Section 3 is all about shifting perspectives. We're looking at principles 13 and 17.
This is where we start playing with the dimensions and the directions of the problem itself.
Principle 13 is the other way around, or as it's often called, inversion.
I love this principle. It forces you to just stop and ask, what if I did the exact opposite of what logic and common sense tell me to do?
The poster child for this has to be the ketchup bottle.
The upside-down bottle. For decades, glass ketchup bottles sat flat on the table. The ketchup, being a non-Newtonian fluid, would settle at the bottom. Getting it out was a battle against physics.
Oh, the struggle was real. You had to shake it, hit the 57 on the neck, stick a knife in there.
The logic was, bottles stand up. The inversion was simply, what if the bottle stood on its head?
You use gravity to keep the ketchup at the nozzle, not at the bottom.
Simple. Brilliant. It solves the problem just by reversing the orientation.
Okay, let's get a bit more technical with it. What about reverse osmosis?
This is a literal inversion of a natural process. So osmosis is nature's way of balancing liquids. Water naturally flows through a membrane from a place of low salt concentration to a place of high salt concentration. It's trying to dilute the salt.
Right. Nature hates imbalance.
But we want fresh water from salt water. We want the water to leave the salt behind.
We want it to go the other way around.
So we apply massive pressure to reverse the process. We force the water against its natural gradient through a special semi-permeable membrane that catches the big salt molecules but lets the smaller water molecules pass through, and we get drinking water.
We are literally forcing nature to run backward for us.
Precisely. Another great one involves self-cleaning filters, say in industrial water systems. Usually water flows one way through a filter to catch debris, but eventually the filter gets clogged up with junk.
So you have to stop the whole machine and change out the filter. Downtime.
You just invert the flow. For just a moment, you pump water backward through the filter. It pushes all the junk off the filter's surface and flushes it away into a wasteline.
That is brilliant. You use the flow itself to clean the thing that cleans the flow.
Construction has a wild one too, top-down construction.
This one hurts my brain a little. How on earth do you build top-down?
Okay, imagine you're in a super dense city like London or Tokyo. You need to dig a deep basement for a new skyscraper, but you can't just dig a giant open pit because the surrounding buildings might collapse into it.
Right. Too risky.
So you build the ground floor slab first. You literally build the roof of the basement before the basement even exists.
And then what?
Then you dig underneath it, you excavate the dirt out through a hole in the slab. As you go down, you cast the next floor down, the B1 level, then you dig under that and cast B2.
So you're digging a hole, but from the inside of the building you're constructing.
Exactly. And at the same time, because you have a stable ground floor slab to work from, you can start building the skyscraper up above ground. You're literally building up and down simultaneously.
That is just so efficient and incredibly complex, I imagine.
It is, but it solves the urban space constraint perfectly.
One more on inversion software, reverse engineering.
This is standard practice now, especially in cybersecurity. Usually you write source code to create a piece of software. Reverse engineering is taking the finished software, the binary code, and analyzing it to figure out how it was written.
It's working backward from the answer to find the question.
Exactly. It's crucial for understanding how a computer virus works so you can stop it, or for making sure your new program is compatible with some old, unsupported legacy system.
Okay, so let's go from backward to up. Principle 17, another dimension.
If you're running out of space in 2D, you go 3D.
This sounds like science fiction, but it's actually just, it's real estate, isn't
That
it?
is. I mean, skyscrapers are the most obvious answer. If the land is expensive, which is a 2D limit, you build up, which is a 3D solution. But let's look at electronics, specifically the supposed death of Moore's Law.
Moore's law says that chips get faster and smaller every year, right?
Roughly, yeah. The number of transistors on a chip doubles about every 2 years. But we're running out of space on the flat 2D silicon wafer. We can't physically make the transistors much smaller without running into, quantum tunneling issues or massive heat problems.
Or hitting a 2D wall.
So we go 3D. We're now seeing multi-layered PCBs, printed circuit boards. Instead of a flat pancake of circuits, it's like a lasagna. You have layers and layers of copper traces stacked on top of each other.
And memory chips, too, I've heard.
Yes. 3D memory stacking. They use something called TSVs, which stands for Through Silicon Vias.
Explain that. What's a VIA?
Usually, chips on a board are connected by wires around the edge. It's a long path. TSVs are microscopic elevator shafts drilled right through the center of the silicon to connect memory chips that are stacked vertically, one on top of the other.
Wow. So you get way more memory in the exact same footprint.
More capacity and actually more speed
Yeah.
because the electrical signals have a much shorter distance to travel. They just have to go up and down, not all the way across a flat board.
It's all about density. It's using the third dimension to escape the limits of the second.
And this applies to data too, right? I mean, I work with spreadsheets all the time. Those are 2D, just rows and columns.
And spreadsheets are great up to a point. But when you have massive amounts of data, say global sales, by product, by region, by quarter, by salesperson, a 2D sheet becomes a nightmare. It's a scroll fest. You get lost.
So we use multi-dimensional databases. You might hear them called OLAP cubes. Imagine a Rubik's Cube, but made of data. You can slice it one way to see sales in Asia, then rotate it to see sales of widgets, then drill down to see Q3 2024. You are navigating the data in 3D space.
That makes analysis so much more intuitive and faster.
It does. And finally, let's talk about foldable tech.
The folding phones and tablets.
Think about what that is, fundamentally. You want a big screen, like a tablet, but you want it to fit in your pocket, like a phone. That's a spatial contradiction.
So you use the dimension of folding to solve it.
You're manipulating the geometry. By folding it, you are using the third dimension, depth, to reduce the 2D footprint, the width and height. When you unfold it, you reclaim that 2D space.
It's clever. It's basically just origami engineering.
Exactly. Innovation often comes from just asking, is there another direction I can move in?
I like that. Okay, we're in the home stretch now, section 4. This is all about time, rhythm, and adaptability. We've got principles 15, 18, 19, and 20.
Right. The world isn't static, so our invention shouldn't be either.
Let's start with principle 15, dynamics. This is all about flexibility, right?
Rigid things break. We said that about the landing gear. Principle 15 says, make the system adjustable. Let it change its own characteristics to match the changing environment.
And the car example here is adaptive suspension.
We talked about the Oleo strut as a great cushion. Adaptive suspension takes it a step further. It changes how it cushions in real time. A lot of high-end cars use something called magnetorheological dampers.
Magneto what now?
It's a special kind of oil that's filled with tiny iron particles. When you apply a magnetic field to it, the iron particles all line up and the oil becomes thicker, almost solid, instantly.
So, if I'm driving on a bumpy road,
The car's sensors detect the bumps, they turn off the magnet, the oil flows freely, and the suspension is soft and cushiony. It just absorbs the road.
but then I hit a sharp corner on a highway at high speed.
If the suspension stays soft, the car will roll and wobble. That's dangerous. So the system hits it with the magnet, the oil thickens up, and the suspension stiffens instantly to keep the car flat and stable through the turn.
It changes its personality based on what I need it to do, moment to moment.
It solves the comfort versus handling contradiction by being dynamic instead of static.
We see this in IT with cloud computing, too, the whole idea of elasticity.
Oh, absolutely. In the old days, you bought a physical server. If you had a quiet day, that server sat idle, which is a waste of money. If you had a Black Friday traffic surge, the server would crash.
That's static capacity.
And cloud computing is dynamic.
When your traffic spikes, the system automatically spins up more virtual servers. They call it auto-scaling. It expands to meet demand. When traffic drops off at 3 a.m., it kills them off to save you money. It shrinks. It adapts to the load in real time.
And this links to Agile development too, doesn't it?
100%. The old Waterfall method of making software was plan everything for a year, build it, then ship it. If the market changed during that year, too bad. You just spent a year perfectly building the wrong thing.
Agile is dynamic.
You work in short sprints, maybe 2 weeks. You build a little, you test it, you get feedback from real users, and then you adjust the plan. You are adaptable to change.
Okay, moving on to principle 18, mechanical vibration. Now, usually if my car is vibrating, that is a bad sign.
Uncontrolled vibration is definitely bad. Controlled oscillation, however, is a superpower.
Explain that.
Think about cleaning. You can scrub a dirty diamond ring with a cloth and some soap, or you can put it in an ultrasonic cleaner.
The little buzzing machine at the jewelry store.
Right. That buzzing sound is high-frequency vibration being passed through the water. It creates millions of microscopic bubbles, a process called cavitation. When those tiny bubbles collapse, they create these tiny, intense shock waves that just blast the dirt off the metal.
So it scrubs in places where a cloth could never reach.
Exactly. It's using vibration to do the work.
What about construction? we're back to concrete again.
When you pour fresh concrete, it's thick and it traps a lot of air bubbles. If you just let it dry with all those bubbles inside, the concrete is weak. It's like structural Swiss cheese.
So you shake it.
You stick a specialized vibrator, like a long poker, into the wet concrete. The vibration makes the concrete thixotropic.
Thixotrop. It's a fancy word that means it temporarily acts like a liquid when you agitate it. The vibration liquefies the concrete. The air bubbles, being light, float to the top and escape, and the heavy aggregate settles into a dense, strong pack.
So you vibrate it to make it more solid. That's a cool paradox.
And you can vibrate the earth, too. Pile driving. Usually you hammer a giant steel pile into the ground. Bang, bang, bang. It's incredibly loud and slow.
And the ground is fighting you the whole way.
But if you use a vibratory hammer, you vibrate the pile at a high frequency. It liquefies the soil particles right around the pile, which reduces the friction almost to zero. The pile just slides in like a hot knife into butter.
That is incredibly satisfying to visualize. And of course, the electric toothbrush.
Sonic here is a perfect example. It's not just the bristles rubbing your teeth. The high-speed vibration creates powerful fluid dynamics in your mouth. It's forcing toothpaste and water into the gaps between your teeth where bristles can't go. The vibration does the cleaning, not your elbow grease.
Okay, next up is Principle 19, periodic action. This one says that pulsing is often better than continuous.
Sometimes, yeah. Our brains and nature in general respond really well to pulses and rhythms.
Like sirens.
If a police siren was just a constant flat hum.
I'd probably just tune it out after a minute. It would just become background noise.
Exactly. A siren wails,
Uh-huh.
It pulses. The change in tone, the rhythm, it demands our attention. It breaks through the noise floor of the city.
It triggers the alarm system in our brains.
And what about health? Intermittent fasting.
This is a huge trend right now.
The idea is that continuous digestion eating all day long constantly taxes the body. By cycling between periods of eating and fasting, which is a periodic action, you trigger certain biological repair processes like autophagy.
You're giving the system a scheduled rest.
And in high-tech engineering, we have pulsed lasers.
For cutting things.
Right. If you try to cut a thin piece of metal with a continuous high-power laser beam, the heat just builds up. You might melt the edges of the metal or warp the whole piece. It gets messy.
So you pulse it instead.
Zap, zap, zap. Short, high-intensity bursts. Each pulse does the cutting, and the tiny pause between pulses allows the material to cool just enough. It's called managing the thermal relaxation time. You get a much cleaner, sharper cut.
But wait a minute. Principle 20 is continuity of useful action. That sounds like the exact opposite of what you just said.
And this is where the critical thinking comes in. TRIZ isn't a simple recipe book. It's a toolkit. Sometimes you need a pulse, like in Principle 19. And sometimes you need nonstop, uninterrupted flow, which is Principle 20.
So when do we want continuity?
You want when starting and stopping is wasteful or dangerous. Think about an assembly line, the whole idea of lean manufacturing.
Okay.
If parts are sitting in a big pile waiting for the next machine, that's inventory. That is waste. You want continuous flow. The part moves seamlessly from station A to B to C without ever stopping.
No cues.
No cues. Or look at power plants. You don't turn a nuclear reactor off at night just because people are sleeping using less electricity.
No, that would take days to restart safely.
Exactly. The startup and shutdown cost and complexity are too high. So you run at 24/7. Water treatment plants are the same way. They have to run continuously to ensure the water supply is safe. Stopping is dangerous.
And in the software world, we have CI/CD.
Continuous integration and continuous deployment.
Instead of releasing one big, risky update once a year, which is a periodic action,
You're releasing tiny updates constantly, sometimes multiple times a day. The code flows continuously to the user. It eliminates the inventory of unfinished code, and it prevents those massive, painful merge conflicts that happen when you wait too long.
and finally, renewables. The sun doesn't shine at night. That is periodic. That's Principle 19. But we need continuous power, which is Principle 20.
So we use batteries. Batteries are the bridge between the two principles. They take the periodic input of the sun and they turn it into a continuous output of electricity at night. They enforce the continuity of useful action when nature itself is being intermittent.
It's all about smoothing out the bumps in the system.
That's a perfect way to put it.
Wow. Okay, we have covered a lot of ground here.
We really have. From 11 to 20.
Let's just try to recap. We started with the safety nets cushioning landing gear with gas and oil and chemically stuffing bigger ions into our phone screens to make them tough.
Then we looked at the environment using gravity with equipotentiality to save our backs, and using curves to save airplanes from ripping apart in the sky.
And we shifted perspectives. flipping the ketchup bottle upside down, reversing osmosis to make drinking water, and building 3D computer chips to cheat the death of Moore's law.
And finally, we wrapped up with time and rhythm adapting with magnetic suspension, vibrating concrete into a temporary liquid state, and balancing the pulse of a laser with the continuity of a nuclear power plant.
It's truly amazing how these patterns just repeat, from a simple ketchup bottle to a nuclear plant.
That's the beauty of TRZ. These aren't just random hacks or clever tricks. They are the fundamental physics of innovation.
So here is the question for you, the listener. We talked about the other way round inversion.
And here is a provocative thought to leave you with. Consider your own life or your work right now. Where are you trying to push a boulder uphill? Where are you fighting gravity, fighting a natural process?
Yeah.
Where are you really struggling?
What would happen if you simply inverted the process? What if you tried to build the roof before the basement? Or are you trying to be 100% perfect when an excessive action, doing a little too much and then trimming it back, would be 10 times faster and easier?
Don't try to paint the edge perfectly. Just paint over the tape.
Exactly. Find your tape.
I love that. Find your tape. Folks, if you enjoyed this mental workout, please go subscribe to @IdeaMechanics9 on YouTube. They are the source of this wisdom, and they have so much more to offer.
Remember, innovation is a repeatable process. Go learn the process.
Thanks so much for listening. We'll see you in the next deep dive.